Okay, let's get into this. For a while now, we've heard the term end-to-end used for large language models.
It's sort of the gold standard, right? The idea that it's all one seamless process.
But the source material we're looking at today suggests there's a bit of a crack in that foundation.
A pretty fundamental one, actually.
We're going to dive into a paper on a new architecture called AutoDeco, which seems to offer a real fix.
It tackles this core issue head-on. The problem is that the final quality of what an LLM generates really hangs on a very manual, almost heuristic process.
You mean the decoding hyperparameters?
The decoding hyperparameters, things like temperature and top, these are settings a person has to choose. The model can't learn them, so calling the whole system end-to-end is, well, a bit of a misnomer.
Let's quickly break this down for anyone listening. When a model is picking its next word, it has this huge list of possibilities. What is temperature doing to that list?
Temperature is basically your creativity dial. A low temperature means the model just picks the most probable, most obvious word. Very predictable, very precise.
And a high temperature.
That flattens everything out. Suddenly, even the less likely, weirder words have a shot. You get more creativity, but you can also get some unreliable results.
And top P, also called nucleus sampling, what's its job?
Top P is more like a filter. It says, okay, only look at the top words that add up to, say, a 90% probability. It's there to stop the model from going completely off the rails.
But someone still has to decide where to set that filter.
Someone does. And this reliance on static, human pick numbers creates a huge bottleneck. It's just not efficient.
The paper even mentions that big commercial providers like DeepSeek recommend totally different settings for different tasks.
One set of parameters for coding, another for creative writing, another for Q&A.
So you have to constantly retune.
You do. It's expensive, it's tedious, and it just doesn't scale. But the problem is actually deeper than just being task-dependent.
Right. This is the main argument, isn't it? The best settings don't just change from task to task. They need to change within a single response.
That's the core idea. A single static setting is always going to be a compromise. Think about asking a model to solve a complicated reasoning problem.
Okay.
In the beginning, it needs to explore, it needs to brainstorm different paths. That calls for high creativity, so a high temperature, a wide top.
But then when it's found the solution and it's time to give the final answer,
Then you want pure precision. You want it to be certain, factual. The temperature should drop to almost zero.
so it needs to switch from brainstorming mode to conclusion mode instantly.
And current models can't. They're stuck with one setting for the whole ride. It's like telling a musician to play an entire song at one single volume.
So that brings us to the proposed solution. What do these researchers do to let the model make these choices for itself?
They introduced AutoDeco. The concept is pretty simple, really. They wanted to turn decoding from a fixed external choice into something the model controls itself, token by token.
So the model learns to self-regulate its own randomness.
In real time, based on the context of what it's trying to say.
So how does that work architecturally? How do they build this into the transformer?
It's actually quite a lightweight addition. They augmented the standard transformer model with two small, dedicated prediction heads.
And these heads are doing what exactly?
At every single step of generating a word, these heads look at the model's current hidden state, what it's thinking at that moment, and they predict two values.
The temperature and the top of.
The temperature, T hat, and the top, P hat, just for that specific token. And those values are then used immediately to generate the very next word.
Okay, but this sounds like it runs right into the roadblock you mentioned earlier. The whole process is non-differentiable. How could they possibly train these heads?
That was the big engineering hurdle. The standard top-teep sampling has this hard cutoff. If a token is outside the threshold, its probability just becomes zero instantly.
Which you can't differentiate, so you can't backpropagate the error. You can't learn. The gradient is just blocked.
The flow is severed. You can't learn from your mistakes if there's no smooth path back to what caused them.
So this is where their big training innovation comes in. They created a differentiable, soft top set.
That's a great way to put it. Instead of a hard on-off switch, think of it more like a smooth dimmer.
So for words outside the top threshold, their probability doesn't just drop to zero?
No, it decays smoothly. They apply a differentiable weight scaling, so a tiny change in the predicted top value from the head leads to a tiny smooth change in the final output probabilities.
And with that smooth connection, the gradient can flow. The heads can actually learn.
It opens up the whole pipeline.
Yeah.
And it allows for a very efficient training strategy. They took pre-trained models, Kuhn, Llama, and they froze them.
So the base model is untouched.
Completely untouched. They only trained the 2 tiny AutoDeco heads on top.
And was this a long, drawn-out process?
Not at all. Because the heads are just simple 2-layer MLPs, they got strong performance in about 400 training steps. It's a very practical upgrade.
And because it's integrated right into the forward pass, the latency hit is tiny. The paper says, what, 1 or 2%?
It's negligible, a true drop-in replacement.
Okay, so let's get to the results. The experimental validation. Did it actually work?
It did. They measured pass at 1 accuracy on 8 different benchmarks, and AutoDeco consistently and substantially beat the standard methods.
Like greedy search and just a default sampling setting.
Right. For example, with the Llama Nematron 8B model, the score went up to 46.05. That's a jump of almost 3.5 absolute points over the baselines.
That's a serious improvement. But the comparison that really stood out to me was the one against the Oracle.
The expert-guided tuning baseline. Yes, this is a key finding.
For you listening, this Oracle is basically the best possible score you could ever get with a static method. It's what happens when you essentially cheat by perfectly tuning your parameters for the test set itself.
It represents an impossible amount of manual labor, a theoretical ceiling for the old way of doing things.
And the result?
AutoDeco, in a single pass with no special tuning, performed nearly identically to that Oracle baseline. The gap was consistently less than 1 point.
So in one go, it automatically achieves what used to require an insane, non-scalable amount of expert effort.
It replaces hundreds of hours of tuning with a 4-megabyte file and a tiny bit of latency. It shows that letting the model decide for itself is just better.
What I thought was maybe even more significant was the generalization. These AutoDeco heads were trained only on math problems, right?
Correct. Exclusively on the deep math dataset. Very structured, very logical stuff.
But then they tested it on completely different things.
Yes, and it showed powerful zero-shot generalization. It worked great on general Q&A, on code generation, on following instructions, tasks it had never been trained to handle.
The paper calls this learning the meta skill of generation.
And the numbers back that up. With one model, the R1 Distill Quinn 7B, the improvement on these general out-of-domain tasks was 4.4 points.
Wow, so it did even better on the tasks it wasn't trained for.
Which really suggests it didn't just learn how to do math, it learned something more fundamental about balancing creativity and precision in language. It learned how to generate text, not just what to generate.
The ablation study was interesting too, even just using one of the heads.
Just predicting temperature, or just top P, on its own still delivered huge gains, 3 to 3.5 points over the baseline. It shows how powerful dynamic control is, even for one parameter.
And all this with, as you said, almost no computational cost. FLOPs are the same, memory is up by a tiny 4 megabytes, latency by 1.7%. It's incredibly efficient.
They managed to embed this intelligence without sacrificing performance.
Okay, which brings us to what might be the most fascinating part of this whole paper. The emergent capability.
This was a genuine surprise. AutoDeco started interpreting natural language commands about how it should behave.
Without being trained to do so.
Not initially, no. They'd give it a prompt with a meta instruction, something about the style of the answer.
Like what?
Something like, I hope the answers can be more innovative and diverse. And when it saw that, the model would spontaneously start predicting higher temperature and top values for itself.
And the opposite worked too. If you ask for certainty.
If you prompted, I hope the answers can be as certain as possible, it would suppress those values. It would internally turn down its own randomness because it understood the intent.
So after they noticed this, they trained it specifically for this.
They did. They fine-tuned it to solidify the behavior, and it became a very dependable feature. With a low diversity command, for instance, the average temperature dropped from 0.72 to 0.61, and it did that 99% of the time.
We're moving from tweaking numbers to just describing the kind of answer you want.
We are. The paper does point out a limitation, though. While the model gets the direction right, more creative, less creative, it doesn't have precise, absolute control yet.
Meaning?
If you ask for no randomness, the temperature drops, but it doesn't go all the way to near zero.
And the researchers think fixing that might require joint training of the whole model, not just the heads.
That's their hypothesis. A deeper integration might be needed for that level of fine-grained control.
So if we pull this all together, we're looking at 3 major contributions. Better performance, almost no overhead, and this foundational step towards controlling generation with natural language.
It takes LLM decoding from this static manual problem and turns it into a dynamic, self-regulating part of the model itself. It really does fix that crack in the end-to-end promise.
It's the first truly practical solution for getting consistently high performance without endless manual tuning.
Every single token is being generated with a sampling strategy optimized for its specific context. That's a huge leap forward.
So the paper notes that getting truly absolute control, like turning randomness completely off on command, might take more work. And it got me thinking, what does it mean for the future of these models if they need to be trained not just on what to say, but on how to feel about the certainty of their own answers, all based on a simple conversational request?